Hello, and welcome to a digital lecture for Calculus 2 at Salt Lake Community College. In this video, we're going to be going through section 7.2, Trigonometric Integrals. Now, in this section, we will really not be introducing any new method of solving integrals. For example, in section 7.1, we talked about integration by parts, which was really a different method to approach different integrals. What we're going to be talking about now are where we have multiple trig functions inside of an integral and how to deal with those, which primarily will involve u substitution, but might not be as straightforward as simply defining something as u and another thing as du. These will be a little bit more complicated and will involve the use of some trigonometric identities. The most common ones that we're going to use I have introduced here at the top. We have the Pythagorean identities, which are going to be some of our most useful tools. We have sine squared x plus cosine squared equals 1, 1 plus cotangent squared equals cosecant squared, and tangent squared plus 1 equals secant squared. These are the most common identities that we will use. However, again, if you just need to memorize one of them, if you have trouble with that, all you really need to do is memorize the first, and you could generate the other two by dividing sine squared or cosine squared from both sides. What we'll also commonly use are the half angle or power identities, depending on who you talk to. These are typically shown as sine squared x equals 1 minus cosine of 2x over 2, so it reduces, gets rid of the power, as well as cosine squared x equals 1 plus cosine of 2x over 2, again, reduces and gets rid of the power. These are also common ones that we will use depending on the situation. Now, moving forward, I will call these the half-angle identities, although typically the half-angle identities are introduced as sine squared of x over 2 equals 1 minus cosine of x over 2, or sometimes even with a square root on both sides. But these are the forms that we're primarily going to use, so I'll just use these ones as they are. We will also be using the following, although these may not be as familiar to you from trigonometry. These are called the product identities, and these are basically what happens if you take the addition and subtraction identities, so the ones that look like sine of a plus or minus b, or also cosine of a plus or minus b, and if you were to combine both of these together. What you would get is just one of the terms that would have sine and cosine in it with some amounts of a or b. And these are the product identities, because we are taking a product of sine times cosine, or cosine times cosine. Now again, these are not the most familiar ones, but there are some patterns here that can help you. There's always a 1/2 involved throughout the entire thing, so that can help. The first term you have, you're going to be subtracting however amount of x you have from each. So if this is sine of 2x times cosine of x, you would have 2 minus 1. So the order there is going to be the same. And if you have two of the same functions, so sine times sine or cosine times cosine, you will have a result that is cosine minus cosine and cosine plus cosine. So we will have the same term, specifically a cosine term. If you have two different terms, sine and cosine, you will then have sine plus sine. So two different terms will give you sines, two of the same terms will give you cosines. So there's a few terms to try to get these down, but I really think practice helps with these, so the more you use them, the better. Now, with those identities in mind, what we're going to address are the 5 what I call the primary forms. These are the forms that you'll most often see, and what we're going to talk about is how we would address them. So we have form 1, which is going to be sine or cosine taken to some power. Form 2 is sine times cosine, each taken to their own powers. Form 3 is sine times cosine with no powers, but with some amounts of m or n, so some amounts of sine and cosine, so like sine of 2x times cosine of 3x. Form 4 will be tangent or cotangent taken to a power, and Form 5 will be tangent times secant, each taken to a power, or cotangent times cosecant, each taken to a power. Also note that Form 5 could also take in mind secant to some power or cosecant to some power with no amounts of tangent or cotangent. So you can also apply these strategies. So these are the most common integrals, and what I have here is a basic outline of the strategies involved. And we're going to go through each of these and have some examples of them. So first what we're going to talk about is Form 1, where you have either sine or cosine taken to some power. And what we have as the general strategy is to pay attention to the power that you have. If the power itself is odd, what we're going to use are the Pythagorean identities. So stuff like sine squared plus cosine squared equals 1. If n is even, what we're going to use are the half-angle identities, the ones that are like sine squared equals 1 minus cosine of 2x over 2. These are the strategies that we're going to use. What we're also going to have to keep in mind here is that we don't want to change everything. We typically want to keep one term separate because we are still going to employ u substitution. And so we're going to try to save, quote unquote, some part of whatever original function I have to use as the du, or the differential. So let's go through a couple examples of these. These ones shouldn't take too long. They're pretty quick. So here we have the integral of cosine cubed x dx. Now we look at that power that we have, we see that the power is to the third power, so the power is odd. Since the power is odd, since 3 is an odd number, what that means is that we're going to look at the strategy and say, okay, we're going to use a Pythagorean identity. Remember here, the Pythagorean identity is sine squared x plus cosine squared x equals 1. Well, if we want to use a Pythagorean identity, we want to use some amount of cosine. So cosine squared x equals 1 minus sine squared x, just subtracting that to the other side. And so what I'm going to do is take this integral and split it up so I have some amount of cosine squared x. I can rewrite this integral as the integral of cosine squared x times cosine of 1x, or just x, dx. That's the same thing as cosine cubed, cosine squared times cosine to the 1 power. This is the part that I'm saving. This is what I'm going to save as du. So that's why we want to save at least one piece of this. If I replace cosine squared x with this identity here, I get the integral of 1 minus sine squared x in parentheses times cosine of x dx. Now what I see is that my new function, whatever I replace, that's what I'm going to focus in on as u, as my u substitution. I'm going to say that u is sine of x, and du then is cosine of x dx, the derivative. Notice that cosine of x dx is what I saved right here. That's the whole point. We're trying to save some part for the differential. That means that this integral simply becomes the integral of parentheses 1 minus sine was u, so this is u squared, times du. So therefore, if we integrate on that, we get u minus 1/3 of u cubed plus c. So if we plug back in u, which was sine, we get sine of x minus 1/3 sine cubed x plus c. And that's what we're looking for. Okay, the more you do these, the faster they'll become, because you'll see a lot of the same patterns. For example, the second one here, we have the integral of sine to the 5th x. Again, don't care what the original function was, I care about the exponent there. I see an exponent of 5, so that means we're dealing with an odd again. So I'm going to split this up, and I'm going to save one bit of this. I can rewrite this integral, instead of sine to the 5th x, what I can rewrite this as is, we can write this as sine to the 4th x times sine of x dx. Or, instead of sine to the 4th x, I could also rewrite this as sine squared of x squared. That's the same thing, and that will allow me to use a u substitution in the way that I did before, by splitting up with Pythagorean identities. I see sine squared of x, so what I'm going to do is I'm going to replace that. I'm going to replace that with the integral of 1 minus cosine squared x squared times sine x dx, in the same way that I did before. We had cosine squared became 1 minus sine squared. We now have sine squared is 1 minus cosine squared. Just reordering the Pythagorean identity for it. Now I can do something similar as before. I could define now u as just what cosine is, so u is cosine. I have du. I don't have exactly sine of x dx, but I would get negative sine x dx. So then I get negative du is sine x dx. So that's going to introduce a negative to the system. So we're going to get negative integral of 1 minus, we defined cosine as u, so u squared, and then du. Again, that negative helps apply for that. Then we can expand that as a pretty simple polynomial if necessary. We can expand that as negative parentheses 1 minus 2u squared plus u to the fourth du. And we should be able to solve that like a typical polynomial and plug cosine in back at the end. I will let you go through and solve that if you so please. Again, that's just going to look like a polynomial of u's, and then you plug cosine x back into that, and then you're done. So you should get 3 terms that involve cosine of x plus c. All right, so we're starting to see how these will work. Now, if we have an even amount, so we have a trig function to an even power, we're not going to use Pythagorean identities. And the reason why we're not going to use Pythagorean identities is if I were to do that here, I would replace sine squared of x with 1 minus cosine squared x dx, and I'm still in the same situation. I've just replaced them now with the Pythagorean identity, and I still have an even power that I don't know what to do with. So it doesn't really help. What we're instead going to do are use the power identities. This one is relatively straightforward because this is just sine squared of x, which is one of the original power identities. Remember that we have the power identity above on the previous page as sine squared of x equals 1 minus cosine of 2x over 2. Again, this is 2x, not squared x. So maybe we'll write that a little bit lower. Cosine of 2x. So then, that's what I can rewrite this as. I can rewrite as, and if I can also move this over 2 as a 1/2 instead to make it a little bit easier. Cosine of 2x. So I can rewrite this integral as 1/2 the integral of 1 minus cosine of 2x dx. And now this integral is solvable. Relatively easy. This 2x, if you want to use a du, if you're not comfortable with doing that, you can. However, you should get 1/2 times 1 will turn into just x, minus cosine x will turn into minus 1/2 sine of 2x plus c. Again, if you're not comfortable with doing that 2x, you can just call u equal to 2x. You can say du equals 2 dx. Divide the 2 over, you get 1/2 du dx. That's where this 1/2 is coming from. Multiply that out, we just get 1/2 x minus 1/4 sine of 2x plus 1/2 times the constant is still a constant of some sort, so plus c still. That's it. Nice and easy. If it isn't just taken to the second power, though, if it's a little bit higher of an even power, like cosine to the 4th x, we are still going to apply power identities, or the half-angle identities. However, it's going to take a little bit more work because it's going to turn them into polynomials instead. For example, here, cosine to the 4th x. Remember that we have that cosine squared x equals 1 plus 1 plus cosine of 2x over 2, or 1/2 times this. So that's what I'm going to do. I'm going to replace this with the integral of 1/2 times 1 plus cosine of 2x squared dx. The only reason, or to the, squared dx, because I'm replacing cosine squared x with just this. Maybe I'll break that up a little bit more, show where I'm getting that. This is just saying cosine to the 4th x is cosine squared x squared dx. So then that's where you get replacing cosine squared x with this. Now I'm keeping the 1/2 separate because I'm just about to take that to a power, and it is itself a constant. So I'm just going to pull that out of the integral to make it a little bit easier. there's no reason I need to have those 1/2s floating around, or what will become 1/4 when I square it. So now, moving down here, I will say 1/4 times the integral of 1 plus cosine 2x squared dx. Okay, and now all we can do right now is just FOIL this out, or distribute this appropriately with the squares. What we get is 1/4 the integral of 1 times 1 will give you 1. 1 times cosine 2x times 2 will give you 2 cosine of 2x. And then cosine of 2x times cosine of 2x will give you cosine squared of 2x dx. So far, so good. Looking at what I have available here, I can integrate this, 2 cosine 2x, that's fine. I can integrate 1, that's pretty easy. Cosine of 2x, though, requires I do this one more time. It requires that I replace cosine of squared of 2x with another half-angle identity. Well, if I have cosine squared of 2x, what that's going to give me is 1/2 times 1 plus, instead of cosine of 2x, it's going to double again and become cosine of 4x. Before it was just a single x, gave me double that. 2x will give me double that. So now this becomes 1/4 the integral of 1 plus 2 cosine of 2x, and this plus cosine squared of 2x will become a plus 1/2 1 plus cosine of 4x dx. Multiplying out and distributing appropriately, we get 1/4 integral. 1/2 plus 1 will give me 1/2, which I'll add to 1 to make 3/2, plus 2 cosine of 2x plus 1/2. Don't forget to distribute. 1/2 cosine of 4x dx. And now I have all my terms, and I should now be able to integrate on this because they're singular cosine terms. So we get 1/4 times 3/2 x plus, when I do this cosine, what I'm going to get is a sine of 2x, and that 2 is actually going to get divided down, so I get sine of 2x. Again, just like before, it would be multiplied by 1/2, so that's why I get that. Plus, this is going to multiply by 1/4, so we get 1/8 overall sine of 4x plus c. And that's what I would be looking for here as an overall solution. Again, you can multiply the 1/4 out, but this should suffice in terms of our end solution. Alright, so it takes a little bit longer the higher the power is. You can imagine that if it was taken to the 6th power, then you might need to split this up multiple times. However, since it's the same process, there's nothing too overly complicated about it. That's how you would deal with the first case. Now let's talk about how you would deal with the second case. The second case is where we have sine times cosine, each taken to their powers. Now, this is also going to be in two different strategies. One, if either m or n are odd, so that means either of the powers are odd. Again, they could be negative odd or positive, doesn't really matter. If either of them are odd, we're simply going to use Pythagorean identities. And whichever one we use a Pythagorean identity on, which is going to be the odd one, we're going to save one piece of that to use as du. Kind of like what we did before in example 2 and 3, where we'd use a Pythagorean identity, but one piece would be saved out, shown either here or here, so that we can have something to use as du. So that's what we're going to do if we see either of those to be odd. If both of them are odd, we actually can pick or choose, whichever one we want to use. If both m and n are even, so if both powers are even, well, we're going to use our half-angle identities, and that's going to take a little bit more time because then it's going to distribute out just like it did in the previous example. So let's see a couple examples of these. We first have sine cubed x cosine to the negative 4th x. So again, focus just on the powers. 3 and negative 4. Well, 3 is odd, negative 4 is even. we have at least one of them being odd, so we have the first instance here. And so all we're going to use is Pythagorean Identities, and we're going to use it on that odd one. I don't need to touch the other one. So, again, remember that we have sine squared x plus cosine squared x equals 1. And so, since I'm going to use it on the odd one, sine cubed x, I should get sine squared x by itself, which is 1 minus cosine squared x. You might already have these memorized, but if you don't, always good to work that out. So I'm going to split up sine cubed x as sine squared x. I have that cosine to the negative fourth of x, and that extra x that I split out, I'll move at the end here. I'm going to move it at the end because this is the piece that I want to save as my differential. So I'm moving that to the end. So far all I did was split up sine cubed into sine squared times sine. Because multiplication is associative and commutative, it doesn't matter where I put them. So I will now replace sine squared with this Pythagorean identity. We have 1 minus cosine squared x times cosine to the negative fourth x times sine x dx. And now what I can do is distribute appropriately. I can distribute this cosine into these. So I get cosine to the negative fourth x minus cosine times 2 plus negative 4 will give me negative 2x times sine x dx. With this, I have everything I need to do just a simple u substitution, setting u as this factor of cosine, and du as, if I take the derivative of that, I get negative sine x dx. That's my u substitution. Again, this is why I save this sine x. That negative is going to make the entire system negative, and we simply have u to the negative fourth minus u to the negative second du. Therefore, we get not negative actually. This is going to become positive. I'll keep the negative there just for distributing purposes. U to the negative fourth, that will increase to u to the negative 3, and then I will do 1 over negative 3. Minus u to the negative 2 becomes u to the negative 1, and then I have 1 over negative 1 there. And then plus c. So overall, this negative will become positive, so I get 1/3. U is cosine, so that's cosine to the negative third power x. This is negative, makes it positive, but the other negative makes that overall negative. Minus cosine to the negative 1 x plus c. And that'd be our overall solution. Now, what this also highlights is how you can also deal with instances that aren't just sine and cosine, if they're secant or cosecant. Well, if they're secant and cosecant mixed with other sine or cosine functions, or a mixture of them, if you notice, cosine to the negative fourth, that's the same thing as secant to the fourth power of x. The exact same function. So, that makes it a lot simpler to deal with in terms of if I have secants and cosecants. I could even change this into secant to the third power minus secant x. A little bit easier. Okay. So, hopefully you're starting to see how that works. For the second one, we have sine to the second power and cosine to the fourth power. Notice again, we focus on those powers. We have that they're both even. That means that we're going to use both of the half-angle identities or the power identities. So this will take a little more room, so I'm going to start the line down here. Sine squared of x, that's just squared x by itself, so that means I should be able to simply replace that with 1 minus cosine of 2x over 2. That is sine squared of x. And then cosine squared x becomes 1 plus cosine of 2x over 2 squared. The reason it becomes squared is the same reason that it did back in example 4. I can replace cosine to the fourth x and replace that with cosine squared x squared, and dx. Okay, this gets a bit gross. I have 1/2 and a 1/2 squared here, so I'm overall going to get a 1/8 outside of this integral. I'll keep that 1 minus cosine 2x by itself for now, but I will expand this 1 plus cosine 2x squared out. That should give me 1 plus 2 cosine of 2x plus cosine squared of 2x. I believe we did that earlier. Then if we multiply everything else out, we get 1 times each of these terms. So we get 1 plus 2 cosine 2x plus cosine squared of 2x. And then we get minus cosine 2x times each of these terms. So that's the 1. And then if I multiply the minus cosine 2x, I get minus cosine 2x minus cosine 2x times cosine of 2x times 2. I get minus 2 cosine squared of 2x. And then minus cosine 2x times cosine squared x will give me minus cosine cubed of 2x dx. All right, so I'm getting a lot of terms here. Putting it all together, 1/8. I have 1 is my only constant. 2 cosine of 2x minus cosine of 2x will just give me a single cosine of 2x. Cosine squared 2x minus 2 cosine squared x will give me minus cosine squared x of 2x, sorry. And then minus cosine cubed of 2x and dx. Okay. Let's clean up one of these. This looked like the square. This was just a 2x. Okay. So notice we have 4 terms. Again, I can solve 1 nicely. Cosine 2x, fine. I could do that integral. Cosine squared of 2x, I can technically do because I can replace that with another 1 plus cosine. This would become 4x over 2. It would get doubled again. But then this minus cosine cubed of 2x, what I could do with that is separate that as its own integral. So I could do minus the integral of cosine cubed 2x dx. And notice that this is just a singular cosine term with an odd exponent. And so what I can do is apply a Pythagorean identity to that one and expand that out so it's solvable. So overall, I should have 1/8 integral of 1 plus cosine 2x minus 1/2 1 plus cosine of 4x dx as my first integral, minus the integral of cosine cubed 2x. I'm going to replace that with the Pythagorean identity to get 1 minus sine squared of 2x times cosine of 2x dx. Now, this top integral is solvable pretty directly. Maybe do a little bit more combining with the constant terms there. And the second term I can solve using U substitution, using the same process that we did in the first case. Or, in the first form. So now everything is solvable. Note, however, it does take some time. These aren't going to be the simplest integrals to do. It may take a while to expand these sines and cosines out, but eventually what you should be able to do is reduce it down so that there are no more exponents, or if there are, they're easier to manage. The bigger the exponent gets, the longer it takes to expand. However, what you really are hoping for is that they have odd exponents. Odd exponents are far simpler to deal with, as in the cases before. It doesn't really matter what the other even one is, because if I have an odd one, I just do a Pythagorean identity, set aside one piece, and do a simple UDU. If they're both even, it takes a little bit longer because I need to take these and distribute them out appropriately. Okay, I'll leave the rest of that to you. Now for this last example, for the second form, we have integral of sine x times cosine x dx. Now this one could actually be considered part of the third case that we'll look at in a moment, but what I want to show is how you can solve this in one direction and how you could solve it in another direction and get different looking answers that are the same. Okay, Notice that both of them have an odd exponent. The exponent technically is 1 because we don't see it. So that means what I should be able to do is use Pythagorean identities as necessary, save one piece, and use that as my du. In this case, I don't have anything taken to more than a 1 power, so I actually don't even need to use any Pythagorean identities. This one I could just do a simple u du substitution. So this is going to be a little bit weird. First, let's do a case where I set u to be sine of x and du to be cosine of x dx. This is probably what most people would do because now du involves just the positive form. That would give us this integral as the integral of u, which is sine, and cosine of x dx, which is du. So that's just the integral of u du. That solves pretty easily as 1/2 u squared plus c, or 1/2 sine squared x plus c. So that would be my solution. Now, alternatively, what if you did it another way? What if you did it as u as cosine of x? Because du would then be negative sine of x dx, which still works. I just moved the negative in there. So now I have negative integral of cosine, which is u, times sine x dx, which is du. So negative u du will give us negative 1/2 u squared plus c, or negative 1/2 cosine squared x plus c. That'd be my solution. Notice that these look different though. And you'll start to notice this if you actually look at answers for some of the questions that you'll be working on in this section. Sometimes the answer that you have won't look exactly like it does as reported elsewhere. That is fine. It could be the exact same solution. For example, let's do this. Let's take that original solution, 1/2 sine squared x, and what I'm going to do, well, plus c, and what I'm going to do is apply, since I see sine squared, I'm going to apply a Pythagorean identity to that. So 1/2 times 1 minus cosine squared x, that would be the Pythagorean identity, plus c. If I distribute it out, that gives me 1/2 minus 1/2 cosine squared x plus c. And this 1/2 is a constant term, so it can combine with just the constant term of c to make another arbitrary constant. So I get overall negative 1/2 cosine squared x plus c. Therefore, what I've shown, if I do another color here, what I've shown is 1/2 sine squared of x plus c is the same thing as negative 1/2 cosine squared x plus c. They're exactly the same function. All right. So that's why sometimes if you do a solution one way where it has multiple solutions, you could get a different answer as is reported, but that doesn't mean that you were wrong. Don't worry about that. Let's go on to form 3 here, the third case. This is where we don't have powers, so kind of like the example we just did in example 7. And what we instead have are some amounts of x for both sine and cosine. So either sine times cosine, both with their own amounts, sine times cosine, that should be sine times sine, sorry. Sine times sine, each with their own amounts, or cosine times cosine. In any of these cases, what we're going to do are use the product identities, which I have repeated here so it can help you with this. So sine times cosine, sine times sine, and cosine times cosine. All right. As an example, we have sine of 2x, cosine of 3x. So since this is sine and cosine, that means that we're dealing with this first instance, sine times cosine. All I'm going to do is simply replace this with the product identity. I could pull the 1/2 outside the integral, but therefore then I get the integral of sine times m minus n, which in this case m is the one on sine, n is the one on cosine. Yes, that is important, so you might need to reorder them if necessary. So sine of m minus n, so 2 minus 3 of x, plus sine of m plus n, so 2 plus 3 of x dx. I guess overall that doesn't necessarily matter about m and n because you're going to add them anyway, so it doesn't matter if you do, well no, it does matter because, yeah, you'll get 2 minus 3. Because sine is an odd function, which means that the negative on the inside doesn't just go away like it would for cosine. So yes, it does matter the order for m and n. But now what we have here is the integral of sine of negative x, because that'd be 2 minus 3, plus sine of 5x dx. So I just have two simple sine functions added together, which I should be able to add. Now, because sine is an odd function, what I'm actually going to do is pull that negative 1 out of here. So I just have negative sine x plus sine of 5x dx. And again, this is because sine of x is odd. That's what allows me to pull the negative out. What I get as a solution for this, for negative sine, that's actually cosine of x. Cosine of x, the derivative is negative sine, minus 1/5 cosine of 5x plus c. And that'd be my overall solution. Or if you multiply the 1/2 out, either way. All right, I have another example here, and notice that the two pieces, m and n, are not just whole numbers. So I have actually one instance here where it's a fraction, another one where it's negative. That's perfectly fine. Notice as well, however, that I have cosine and sine in reverse order. What that first means then is that I need to consider this as sine of negative 4x times cosine of 3/2 x dx. So that means that if I now have sine in this order, now it's going to help me dictate how I would write out the rest of the product identity. Again, I'm going to pull the 1/2 outside the integral, but what I should get after this is sine times m minus n. So I get negative 4 minus 3/2 of x. And then I get plus sine of m plus n. So negative 4 plus 3/2 of x dx. That gives me 1/2 of negative 4 minus 3/2, or negative 4 is also negative 8/2. I want to think about fractions. So that will give me negative 11/2 of x plus sine of negative 8/2 plus 3/2 will give me negative 5/2 x dx. Since, again, sine is odd, what we can actually do is pull that negative out. So I could say minus sine and minus sine. And then finish off with the integral. This is sine of 1/2 x will give me 1 over 1/2 of cosine x, or cosine of 1/2 x, positive because it was a negative sign. And then minus sine will again give me a positive cosine. It will give me a positive 1 over 5/2 of cosine of 5/2 x plus c. If we multiply that out entirely, 1 over 1/2 gives me 2, times 1/2 just gives me 1. So cosine of 1/2 x. 1 over 5/2 gives me 2/5, times 1/2 will just give me 1/5. Cosine of 5/2 x plus c. And that's it. All right, these aren't too bad. Just got to kind of get used to the product identities. You might need to start memorizing those. Move on to Form 4 and Form 5 on the last page here. Form 4 is where you have tangent or cotangent taken to some power. In order to solve both of these, all we need to use are the Pythagorean identities. Note that it doesn't actually matter for tangent or cotangent what power you have. You don't need to worry about that, because actually in these cases, what we typically want to have stick around are some even amount of that power anyway. That's typically what we'll use as the integral piece. You'll see a couple examples here. So cotangent to the fourth power. What I'm going to do is simply use a Pythagorean identity. Note that the Pythagorean identity we have for cotangent is 1 plus cotangent squared x equals cosecant squared x. So what I'm going to do this kind of slowly. What I'm going to do is split this up as the integral of cotangent squared x times cotangent squared x dx. And what I'm going to do is just replace the squared part of it, one of them, with the Pythagorean identity. I don't want to replace all of it with the Pythagorean identity because I want some amount of the original function to stick around. That's always the case. Subtract 1 over, and what we get is the integral of, maybe I'll move that to the side actually, equals the integral of cotangent squared x. I'm going to keep that around for now. And cotangent squared is going to become cosecant squared x minus 1 dx. Okay, so far so good. Now, if I distribute this out, what I get is the integral of cotangent squared x times cosecant squared x. And then I get cotangent squared minus 1, which I'm actually going to separate out as its own integral, as minus the integral of cotangent squared x dx. Okay. Now, the reason I do this is because cotangent squared x I can split out a little bit more if necessary, and I can make this the integral of cotangent squared x plus times cosecant squared x dx minus, and this one I'm going to split up again as cosecant squared x minus 1 dx. All right. Now, if we notice, if we do some u substitution here, I could do the integral of cosecant squared. That just gives me cotangent. I could do the integral of 1. That just gives me x. That's fine. However, this first integral of cotangent times cosecant, I'm actually going to do a u substitution. And that's because if I have u as cotangent of x, the derivative of cotangent is cosecant squared x dx. Notice that that's the piece that I have right here. So this is going to be a u du situation, where it's going to be u squared x times dx, which will give me 1/3 of u squared, which will be cotangent cubed, or cotangent cubed x, minus the integral of cosecant squared. Integral of cosecant just gives me cotangent. It actually gives me positive cotangent, sorry. Which actually means that the derivative of cotangent is negative cosecant squared, which means that this is a negative 1/3. Plus cotangent of x, that's the integral of negative cosecant. And then negative and the negative makes it positive, and so we get a positive x plus c. So we get that as our integral. Okay. Notice as I made a little bit mistake there, but we caught it pretty quick. Doing the derivative of cotangent gives me negative cosecant. If you're doing that for tangent, you get a positive secant, so it's a little bit of a different one. Okay. So note that that's what happens if you have an even amount of cotangent or tangent. It would actually solve in a very similar way, where you're always trying to keep a squared amount of cosecant or secant because that's what you need as your differential piece. For tangent to the third x, we have an odd power. We're still going to use Pythagorean identities. However, we can't do it on all of it. Obviously, there's going to be one tangent left over. So I'll write out the Pythagorean theorem again for this. This is going to be tan squared x plus 1 equals secant squared x. That's what we're using. So here I will split this up into tangent squared x times tangent x dx. Tangent squared we can replace with secant squared minus 1. Minus 1 times tangent x dx. And this first part, if I multiply this out, I get secant squared x times tangent x. This is actually really good because the derivative of tangent is secant squared, so this integral would be good. The rest of that, though, would be minus the integral of tangent x dx. I'm splitting this up because I'm doing these in different ways. This first one would be a u du situation. The second one is just its own integral, which would become natural log of secant. This one, if we do as a u du situation, we would set u as tangent x. Du would be secant squared, positive this time. Again, apologies for the previous error. So that would be the integral of u du minus the integral of tangent is actually just natural log of secant plus c. And so this one's going to give us 1/2 u du, u squared du, sorry, 1/2 u squared, minus natural log of secant plus c. And again, that's going to give us another constant, which just combines with the other one. So we get as a final answer 1/2 u, which was tangent, so 1/2 tangent squared x minus natural log of secant x plus c. And that's it. It's all about using those identities and use substitution. All right, a couple more examples here. We have form 5. This is where we're going to have tangent times secant, so we have both of them showing up now. And we have some amounts of tangent, some amounts of secants. And we have cotangent times cosecants and some amounts of each of those, so each taken to their powers. Now these ones we're going to use Pythagorean identities. However, we have some recommendations. If n is even, so that means if secant or cosecant have an even power, you want to save two factors of that. So you want to save secant squared or cosecant squared, because that will be your differential piece. If m is odd, so if tangent or cotangent odd, you're actually going to save a single factor of that term, because that's going to help you solve the rest of the situation. So a little bit of a more case-by-case basis here. Let's see a couple examples. We have tangent to the negative 3/2 x, that's neither odd nor even, and we have secant to the 4th x, that's even. So that's going to fall into the first case, where we have an even amount of secant or cosecant, and so what we're going to do is make sure that we save some amount of that. We're going to save some secant squared amount of that, because that will involve my du piece. These I actually think are easier than the previous ones, because these tend to simply be u du situations. Okay, so what we're going to do is split this up as tangent to the negative 3/2 x. We're going to split this up as secant squared x and secant squared x dx. Again, this is what I'm going to save as my differential piece, so set that aside. If I substitute in a Pythagorean identity for secant squared, what we get is 1 plus tangent squared times secant squared x dx. And then what I can do is distribute out this tangent to negative 3/2 x to get some terms. We can get tangent negative 3/2 times 1, just gives me tangent to the negative 3/2 x. Tangent to negative 3/2 times tangent to the second x, they just add those terms together, so we get 1/2 as an exponent. And we have secant squared x still on the outside. Now we can do this as u equals tangent, because the derivative of tangent is secant squared x dx. And so now this is the integral of u to the negative 3/2 plus u to the 1/2 times du. Nice and easy. Now solving this, the exponent would increase to u to the negative 1/2. We have 1 over that. Plus 1/2 would increase to u to the 3/2, and so we have 1 over that. Plus c. and then substitute in our tangent functions, which we set as u, to get -2 times tangent to -1/2 x plus 2/3 tangent to the 3/2 x plus c. And so that would be that. Notice how much easier that was. We just saved secant squared x, separated it out, and dealt with it as a normal UDU situation by making it a polynomial. Okay. Last example. Now, one thing that you're going to need to keep in mind for this one, just moving into it, is that if you're doing the derivative of cosecant, because we're going to do this in a moment, the derivative of cosecant of x is negative cosecant x cotangent x dx, technically. Just remember this because we are about to use it. And the reason why we're about to use it is because we're going to save both terms. Notice that at the top, I said if m is odd, you're going to save a single factor of that term, but you're also going to save a single factor of the other. So you're going to save a single factor of both cotangent and cosecant. So what we're going to do here is separate out this piece of cosecant and cotangent. So I'm going to rewrite this so I have cotangent squared x. If I take out one instance of cosecant, I get cosecant to -3/2 x. And I'm going to have both a cotangent piece out here and a cosecant piece out here. So I'm separating this out to save for later. This is my differential piece that I want. Now what I can do is replace cotangent squared x with a Pythagorean identity and say the integral of cotangent squared x, which I can replace with cosecant squared x minus 1, times cosecant to 3/2 x times this saved piece. Now then, if I multiply that out, I get the integral of cosecant squared times cosecant to -3/2 will give me cosecant to the positive 1/2 of x minus cosecant to -3/2 of x times cotangent cosecant of dx. And now we could do our UDU. I could set u to be, maybe I'll do it over here. I could set u to be cosecant of x and du to be negative cosecant x cotangent x dx. So that means all I need to do is introduce a negative in front of this integral. We get negative integral of u to the 1/2 minus u to the -3/2 du. And now this solves just like the last one. So negative, this becomes u to the 3/2, so I have 1 over 3/2 here, minus this becomes u to the -1/2, so I have 1 over -1/2 here, plus c. Which overall will give me 2/3 u, which is cosecant, so cosecant to the 3/2 of x. Minus makes positive, but this other minus makes it negative. 2 cosecant of -1/2 of x plus c. Again, the minus would apply to the c, but c is an arbitrary constant, positive or negative, so it doesn't matter. So that's what we'd be looking for, a negative on this 2/3 as well. All right, and that's it. So that's how you would deal with these kinds of forms. We have a few different ones you want to keep in mind, and they approach pretty similarly. They tend to either be using the Pythagorean or half-angle identities. There's just the one instance where you have some amounts of either sines and cosines multiplied together where we use the product identities. With that said, I recommend to go out and try the homework on your own. If you have any comments or if you have any questions, feel free to put those into the comments down below or ask your instructor directly. With that said, I hope you have a nice day.